Welcome back, everyone. Today we're going to talk about counting. Though it may sound trivial, it's important that you're able to count the possible outcomes of a particular scenario. In this section, we're going to talk about ways to count possible outcomes and then how to use them to determine probabilities. The first technique is one that you saw briefly in the previous example, which is a tree diagram. A tree diagram just uses branches, similar to a flowchart, to list all of the outcomes of possible probability experiments that are done in some type of sequence. To draw a tree diagram, we just start with the branches from a single point and we extend outward for each consecutive part of the experiment until we're finished. So here we have a tree diagram. We have a family that's going to have 3 children. We want to determine what are the possible outcomes for the genders of the 3 children. So the first child is either a boy or a girl. And then we have the same for the second child. And we just start with each branch. And at each point, we can have either a boy or a girl. And now, to determine the possible outcomes, we'll just follow the branches. So you could have 3 boys, or 2 boys and a girl, or boy, a girl, and a boy, and so on. We just follow the branches to get all of our possible outcomes. And when we're finished, we'll see that we have 8 total outcomes when a family is going to have 3 children. So the sample space from our previous example includes the list above. So what's the probability that a family will have exactly 2 boys? So now that we've been able to write out all of the possible outcomes from this probability experiment, we can now identify which outcomes have exactly 2 boys. So here's 1, 2, 3. So there are 3 possible outcomes out of 8 total, which is equal to 0.375 or 37.5%. So there's a 37.5% probability that a family will have exactly 2 boys if they have 3 children. If we want to determine the probability that the family will have at least 2 girls, well, we want 2 girls or more. So we can have 3 girls, or 2 girls, 2 girls. And so there are 4 possible ways that can happen out of an 8 total, or a 50% chance, 0.5, that the family has at least 2 girls. So let's practice with another tree diagram. We've got a soda machine that can dispense 2 different products of drinks, 2 different sizes of drinks, and then 3 different types of drinks. And we want to determine the sample space for this particular experiment if we're just going to choose a drink at random. So if we're going to choose a drink, then our first choice is Coke or Pepsi. And then from those, we can choose either a 12 ounce or a 20 ounce. And then from each of these, we can each choose one of 3 different drinks. Either a cola, a diet cola, or a lemon lime drink. Cola, diet cola. Cola, diet cola, lemon lime. And so now we can determine the total possible outcomes of this particular probability experiment. Based on the number of branches in the tree, we know that we're going to have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different outcomes. And we want to know what's the probability of choosing at random a diet cola. Well, out of 12 of those outcomes, 1, 2, 3, 4 are diet colas. And so the probability is 4 out of 12, or 1/3, or 33.33%. So a coin's flipped, and then we roll a die. We're going to draw another tree diagram, and we're going to find the probability of getting heads on the coin and an even number on the die. So we're going to flip a coin, and if we flip a coin, then we either get heads or we get tails. And then after we flip a coin, we're going to roll a die. And so we can have 6 different outcomes in each situation here. 1, 2, 3, 4, 5, 6. And so we can write the sample space. We could have heads and then roll a 1, heads, roll a 2, 3, and so on. And then we could have tails and do the same thing. So we know now how many outcomes we have, and we know what all of our possible outcomes are. We want to find the probability of getting heads on the coin and an even number on the die. Well, heads are all over here on the left, even numbers, 2, 4, and 6. And so there are 3 ways to get heads on the coin and an even number on the die. Out of 12 total outcomes, which is 1/4 or 0.25. So there's a 25% chance of getting heads on the coin and rolling an even number on the die. Another way to determine the sample space is just to use a table to essentially show all of the possible outcomes and then use that table to find the outcomes of interest. Here we have a table of all the cards in a standard deck of cards. There are a total of 52 cards in a standard deck. We're going to use these to answer some questions. So, given our table, what's the probability of picking a jack from the deck? Well, there are 4 jacks in the deck out of 52 cards, which is 1 out of 13, or if we write this as a decimal, 0.0769, or 7.69%. So there's a 7.69% chance that you would choose a jack if you just picked a card at random. If we want to determine the probability of picking a black card that's between 2 and 7, well, there are this many black cards between 2 and 7. 1, 2, 3, 4, 5, 6. So there's 12 out of 52, which is 0.2308 or 23.08%. So there's a 23.08% or about 23% chance that you'll pick a black card between 2 and 7. If we want to find the probability of choosing 3 or a diamond, here are all of our 3s, and then all of the diamonds. And if we just count all of those, there's 13 diamonds and then 1, 2, 3 other 3s. That gives us a total of 16 out of the 52 cards in the deck, which is 0.3077 or 30.77% chance of choosing a 3 or a diamond. And we did this one on the last slide. So we can do a similar thing if we were to roll 2 dice. So when we roll 2 dice, if we add up the numbers that are on the dice, we can consider that sum to be the outcome, right? So if you roll 2 1s and you add up those numbers, you get a 2. Roll a 1 and a 2 and you get 3, and so on. And so we can use this table to answer some similar questions. And just remember that in this case, there are 36 possible outcomes. So what's the probability that you would roll an 8? Well, there are 1, 2, 3, 4, 5 ways to roll an 8. 5 over 36, 0.1389 or 13.89%. The probability of rolling a number less than 5. Well, only 2, 3, and 4 are less than 5, so 2, 3, and 4. And so there's 1, 2, 3, 4, 5, 6 ways you can roll a number less than 5 out of 36 possible outcomes, which is 1/6 or 0.1667 or again 16.67%. What's the probability of rolling doubles? That's a little bit of a different question, but we can still figure this part of it out. We know that doubles would mean the same number, so 1 and 1 would be 2. 2 and 2 would be 4. And you see that it forms all of these outcomes here. And so there are 6 possible ways to roll doubles, to roll the same number on both dice. Out of 36 total outcomes, which again is 1/6 or 16.67%. The probability of rolling a 7 or an 11, well, there's 1, 2, 3, 4, 5, 6 ways to get 7 and 2 ways to get 11. So that's 8 possibilities out of 36, which is 0.222 or 22.22%. So even though tree diagrams are helpful, they are not going to be the easiest way to do everything. As you can tell, as there are more possibilities, they become larger and larger and harder to keep up with. But there's a way to solve these problems by just using what's known as the fundamental counting principle. If you have a sequence of n procedures, then if the first occurs in some number of ways and the second in some number of ways, right? So if the first has some amount of possibilities, the second has some amount of possibilities, and we're doing these things in sequence, then the total number of ways that you can have, the total possible outcomes, is just the product of all those numbers. So for example, with the coin and the die before, we know that there's 2 possibilities when you flip a coin, heads or tails. There are 6 possibilities when you roll a die, for a total of 12 possible outcomes. And so when you multiply those 2, you can determine the number of outcomes without having to write them all out. So you go to a fast food restaurant, and you want to order a burger. Your choices include a hamburger, a cheeseburger, or a chicken sandwich. You can also have one choice of a side, so either fries, tater tots, fruits, or vegetables. And you can choose a soda or a bottle of water. So first of all, how many different meals are possible? To determine that, we just need to know how many different options we have at each point where we make a choice. So for our sandwich, there are 3 different options: a hamburger, a cheeseburger, or a chicken sandwich. For our side, there are 4 different options: fries, tater tots, vegetables, or fruit. And then for your drink, there are 2 options: soda or a bottle of water, which means the total number of meals that are possible is going to be 24. So if we choose a meal at random, what's the probability that that meal contains a hamburger? Well, we may not know exactly how many outcomes have a hamburger in them, but we can figure that out still using the counting principle. So let's say instead of having a choice of a sandwich, we just have one sandwich, a hamburger. That means we could have up to 8 possible meals with a hamburger. Hamburger with fries and a soda, hamburger with tater tots and a soda, so on. And so to find the probability that the meal contains a hamburger, well, there are 8 possible meals out of 24 total, which is 1/3. 4.33 repeats forever, or 33.33%. This should make somewhat intuitive sense to you in the fact that if you have 3 choices of a sandwich and you randomly pick one, there's going to be a 1/3 chance you wind up with the one with the hamburger in it. So we have a company with 412 employees. They're designing new ID badges. Each badge is going to be coded with a 4-letter sequence, chosen from the letters A, B, C, D, and E. Will there be enough badges so that everyone gets a different code? Well, we can determine how many badges they can make by the number of choices that they have. So for the first letter, and let's write this as letter 1. It's a 4-letter code. So letter 1, 2, 3, and 4. For the first letter, you have 5 options, A, B, C, D, and E. For the second letter, you have 5 options. For the third, 5 options. And for the fourth, 5 options. If we multiply all of these together, we get what amounts to 5 to the 4th power. And we're multiplying all of these. And so there's a possibility of having 625 badges. Now in this case, we're allowing the letters to be used more than once. But what if we can't use the same letter more than once? Is there still enough if we can't repeat the letters? Right, so again, letter 1, 2, 3, and 4. So for letter 1, we can choose A, B, C, D, or E. So we have 5 choices here. So let's just say we choose A. We can't use A again, which means at the second letter, we have to choose a different one, B, C, D, or E. And so here we have 4 options. If we choose E, we're left on the third letter to have 3 options. If we then choose C, we're left with only 2. And so if we multiply these together, there are only 120 possibilities for badges at the company. So the letters are going to have to repeat. Finally, this last example is just to show you another way of using the counting principle with something everybody's familiar with. Similar to the ID badges, we all have social security numbers. They're made up of 9 different digits. Digit 1, 2, 3, 4, 5, 6, 7, 8, and 9. If we want to know how many different social security numbers are possible, we can determine that by just using the counting principle. For the first digit, you can choose numbers 0 through 9. Okay, so there's 10 choices. And if we can repeat the numbers, which we can, there will be 10 choices for each number. That's possible. Which leaves us with 10 to the 9th power, or 1 billion possible social security numbers. Please let me know if you have any questions.